Hello everyone, and welcome to this detailed explanation of the research paper titled, MOM, Memory Efficient Offloaded Mini-Sequence Inference for Long Context Language Models. This work, authored by Junyang Zhang, Tianyi Zhu, Cheng Luo, and Anima Anandkumar from the California Institute of Technology, presents an innovative approach to handling the memory challenges in long context language models. Long context language models, like those based on the transformer architecture, are incredibly powerful because they can process and understand extended sequences of text, capturing complex dependencies across thousands or even millions of tokens. However, deploying these models for inference is tricky due to their high demands on GPU memory. The self-attention mechanism in transformers scales quadratically with sequence length, leading to massive memory usage for both computations and storing intermediate values. In this paper, the researchers introduce a method called Memory Efficient Offloaded Mini-Sequence Inference, or MOM, to address these issues. MOM is designed to make inference more efficient by reducing peak GPU memory usage without sacrificing accuracy or performance. It achieves this by combining two key strategies: partitioning critical layers into smaller, mini-sequences, and integrating with KV cache offloading. First, let's break down what KV cache offloading means. In language models, the KV cache refers to the key and value tensors generated during the attention mechanism. These are typically stored on the GPU to speed up processing, but they can consume a lot of memory, especially for long sequences. MOM offloads this KV cache from the GPU to the CPU during the prefill stage, which is when the model initially processes the input prompt. Then, it reloads the necessary parts during the decode stage, where the model generates output tokens one by one. This offloading helps free up GPU memory significantly. The second part of MOM involves partitioning the inputs to the model's multi-layer perceptron, or MLP, layers into smaller mini-sequences. The MLP layers are often the biggest memory hogs because they deal with large intermediate activations. By breaking these down into smaller chunks, MOM processes them in a way that minimizes peak memory usage. Importantly, it only processes one token at the final MLP layer and the language model head, which keeps computational overhead low and maintains efficient throughput. The paper demonstrates MOM's effectiveness through experiments on various models, including Llama, Qwen, and Mistral families. For instance, on the Meta Llama -3.2-8b model, MOM extends the maximum context length from 155,000 tokens to 455,000 tokens on a single A100 GPU with 80 GB of memory. That's a substantial improvement, allowing the model to handle much longer inputs without running out of memory. And crucially, the outputs remain identical to the standard model, meaning there's no loss in accuracy. In terms of memory savings, MOM reduces peak memory usage by over 50% on average across the tested models. This is achieved while keeping throughput, essentially, the speed of generating outputs, highly competitive. The method introduces minimal computational overhead because it streamlines the processing of the last layers. To put this in context, the paper compares MOM to traditional chunked prefill methods, which divide the input into chunks to manage memory. MOM outperforms these by extending context length by about 35% more. More importantly, it drastically cuts down memory consumption during the prefill stage, which has long been the biggest bottleneck in inference. By eliminating this dominant memory issue, MOM shifts the focus of future research from optimizing the prefill stage to improving efficiency in the decode stage, particularly with residual KV cache management. The researchers ground their work in the broader landscape of language model optimizations. They reference earlier techniques like flash attention, which speeds up attention computations, and methods like linformer or reformer, which reduce the quadratic complexity of attention. There's also mention of mini-sequence transformer, or MST, which uses gradient checkpointing for training but isn't suitable for inference due to added overhead. In contrast, MOM is tailored specifically for inference, avoiding those pitfalls. Another related approach is HEADINFER, which offloads KV caches on a headwise basis, but it suffers from severe speed degradation, making it up to 7 to 8 times slower than standard models. MOM avoids this by being more efficient in its offloading and partitioning, ensuring that decoding remains fast. Figure 1 in the paper illustrates this clearly, showing a direct comparison of GPU memory usage for the standard Llama 3 model versus Llama 3 with MOM on a 64,000 token input context. The reduction in VRAM usage is evident, highlighting how MOM makes long context inference feasible on hardware that's more affordable, like consumer-grade GPUs. This breakthrough is timely, given the growing emphasis on test-time computations in large language models. Techniques like few-shot learning, beam search, and advanced prompting strategies increase inference demands, and models like ChatGPT are pushing the boundaries of dynamic context expansion. By optimizing memory usage, MOM paves the way for deploying these sophisticated methods on limited hardware without prohibitive costs. In the introduction, the paper reviews the evolution of transformer models and their limitations. It notes how innovations in training, such as zero and deep speed, have scaled models up, but inference remains a challenge. The authors argue that with MOM, the field can redirect efforts toward more efficient decoding strategies, potentially unlocking new applications in areas like document summarization, long-form question answering, and interactive AI systems. Overall, MOM represents a significant step forward in making long-context language models practical for real-world use. By tackling memory bottlenecks head-on, it ensures that these models can handle extended contexts efficiently, opening doors for more accessible and powerful AI deployments.